So we're going to go over the binary to hexadecimal converter logic. So here we have the XDC file, which is the constraint file. We've got the clock, we've got data, which represents the 16 switches below the 7-segment display. We've got the 7 segments, we've got the 8 anodes, because you've got 8 different digits. And then you've got 16 LEDs, which are right above the buttons, but below the 7-segment display to allow for easy debugging as well as recording, because it can be difficult to see the switches and the 7-segment display at the same time. Followed by the center button, which we use to toggle between hexadecimal and decimal. So here we've got our imports, we've got the different ports as specified before. You've got your 7-segment display in form of seg and anode. You've got your switches and data. You've got the LEDs right above the switches here. And finally, you've got your button and your clock. Here we have a bunch of variables. Digit is the anode that we want to point at. Timer is a sort of a counter that we increment every time the clock ticks, for reasons that we'll discuss later. You've got count, which is a counter, used sort of as a for loop, but not really. You've got this actually an unused signal, we'll get rid of that. And then you've got value. This is the value of each different segment. So the value is only actually goes to 0 to 15, which is 0 to F, but we include a 16th value for the integer to take on to allow error states or not valid states for reasons that we'll discuss later. Next we move on to overall value. This is essentially the decimal value of the input. It ranges between 0 and 65535, which is between 0 and 2 to the 16th quantity minus 1, which is the maximum number you can represent with 16 bits. Next you've got copy. It's essentially just a copy of the overall value used in the computation. Then you've got a temporary variable. This one's also unused actually. Followed by I, which is a second counter separate from CMT count. And you've got your base, which could theoretically be any number between 1 and 16 because we don't have a way to display values higher than 16. Sure, with 7-segment display it's possible 2 to the 7 minus 1 possible ways or values can be outputted using that display, but human readable, not really. From there we move on to the actual behavioral. So we have the LEDs, which we just set to the input switches to allow debugging and easy viewing of what you've input and what the output should be. We're going to come back to this. This is the meat and bones of the actual converter. Here we just have a basic 2 processes that set the display input or output. So here we select the anode that we want to work with. We only ever set 1 to 0 at a time, as you can see. There's a possible efficiency loss here because if two digits have the same value, then it would be more efficient to enable both of their anodes at the same time, set the segment, and then disable both anodes. But we don't do that right now. And here we have 8 different digits, and we have an error state which allows all of the lights to be turned off, mostly for debugging purposes. And similarly with the segments, 0 to 15, that's 16 possible states, but then we have a 17th possible state where we just turn off the segment entirely. This theoretically could be used to remove leading zeros, but we don't do that right now. Just mostly for debugging. Now we get into the main logic. So as you can see, we wait until the rising edge, and if the timer is under 2474, then we actually don't really do anything. We just zero out the overall value and set the initial state for this counter. Now, the reason for this is actually because the transistors that drive the display have a rise and fall time, which causes them to have sort of a ghosting effect if you do not give them some delay. So for that reason, we have this delay. It basically, the main reason that that ghosting effect happens is that the transistor will be between two states, which means that if you try to drive a signal at the same time as you are between driving that transistor, you will end up affecting more than just the one anode that you intended to. So now we sort of get into this loop that we have over here. It's not really a loop, but it acts as one. The reason we can't actually use for loops in VHDL is that it has to do with the way VHDL synthesizes loops and runs them. So we essentially make our own loop by using I as the control variable, 0 to 15. Of course, we do need to set this ourselves. It's 15 away from 2474, which is how that happens to work out. So essentially what we do is we say if the switch is enabled, then we increment overall value by 2 to the I. So for example, if the 0th switch is enabled, we increment it by 2 to the 0, which is 1. If the second switch is enabled, which would be index 1, with the way we have it labeled, then we would increment by 2 to the 1, which is 2, and so on and so forth. What this allows us to do is because the integer type allows us to work in decimal, it allows for us to easily output it as decimal and also convert it to hexadecimal. So this is basically the input side, right, in this one statement right here. From there, we just decrement I each time, so we go from 15 down to 0, and we've done the math so that it doesn't actually reach, it goes 15 all the way down to 0, it does not loop back to 15, as you would happen if you exceeded the range of one of these integers. From there, we have a bunch of else ifs. Now, the reason that this happens is that, again, for loops, not very usable in our case, and also because with how VHDL does assignment of signals. So if we try to assign all these signals at the same time, we have digit equals 8, digit equals count. Only the last assignment will work or actually take place. It won't happen sequentially. And that causes issues for us. So instead what we do is we say every time the process is run, we'll only run one statement at a time. That essentially causes it to behave as you'd expect a loop would behave in other programming languages. So from there we just set the digit to 8, which is invalid because we only have 0 to 7 digits. And what that does is it sets the anode to all ones. Basically make sure that we're not displaying anything. Next, we set the value to 16, which is another error state for value, and that basically just outputs none of the segments to be on, which is useful in debugging, and it, again, could be used in suppressing leading zeros, but we don't do that right now. Then we just move the counter variable to digit. As you can see, count is initialized to 0 over here. It basically allows us to just assign the variable to digit. We could actually do this without a count variable and just directly operate on digit. But again, for debugging, it's useful. Next, we assign the temporary variable as copy divided by base. So this is very easy to explain with decimal. So for example, if our input is 1234, we divide by 10. Mathematically it's 123.4, but because we're using integer data types, it's just 123. Then we subtract copy base times temp. this is the same temp that we used over here. And the reason that we do that is it allows us to essentially calculate the mod base, or the value mod base. So 1234, we subtract 1230, which gives us 4, essentially what mod does. Once we have that, we assign that to value. Value is now 4, and that's the reason we do this is actually because allowing us to use count allows us to work our digits right to left, which means that we don't need to store the value of the digits before displaying them. It's very simple. We just display them as we calculate them. So once we've determined the value, then we just divide by 10, or in this case 10 because the base is 10 to start out with, which makes 123, which basically prepares this entire thing for the next iteration of the loop. And this loop doesn't occur until the timer goes all the way back from 0 to the last state, which is 2497. The reason that we have this again is to prevent ghosting. So after we do that, we just go over here. If the count is invalid, then we set it back to 0. And we also set the copy as the original value, because if you remember, we've been dividing copy by the base every time, which is modifying it. So if the user input has changed between the last iteration of the loop and the next iteration, we want to bring it to be current by changing it to copy. From there, we have the button logic, which essentially says if the button is pressed, and then we handle this if statement right there. So if the button's been pressed, then we just switch between 10 and 16. If it's 10, we set it to 16. Otherwise, we set it to 10. Very simple. And that's the meat and bones of our binary to hexadecimal converter. Thanks for watching.